Light is a fascinating form of energy that allows us to see and perceive the world around us. Scientifically, light is an electromagnetic wave, and the portion we can see falls within the visible spectrum, with wavelengths ranging from about 400 to 750 nanometers. We see objects either because they emit their own light, like the sun or a light bulb, or because they reflect light from other sources, such as the moon. Luminous objects produce their own light, while non-luminous objects can only be seen when illuminated by something else. This fundamental property of light sets the stage for the study of optics, the branch of physics dedicated to understanding how light behaves and interacts with matter. Optics is the branch of physics that explores the behavior and properties of light, including its interactions with matter and the construction of instruments that use or detect it. Optics covers not only visible light but also ultraviolet and infrared light, as well as other forms of electromagnetic radiation like X-rays and microwaves, which share similar properties. The field of optics is divided into two main areas: physical or wave optics, which deals with the wave nature of light and explains phenomena like diffraction and interference, and geometrical or ray optics, which focuses on image formation using lenses and mirrors. In this video, we will focus primarily on geometrical optics. Throughout history, scientists have proposed various theories to explain the nature of light. Newton's corpuscular theory suggested that light consists of tiny particles called corpuscles, which travel in straight lines at high speeds. Huygens, on the other hand, proposed the wave theory, stating that light travels as waves through a hypothetical medium called ether. Later, the quantum theory introduced by Max Planck described light as being made up of energy packets called quanta or photons. Each theory contributed to our understanding of light, and today we know that light exhibits both wave-like and particle-like properties, a concept known as wave-particle duality. Geometrical optics, also known as ray optics, describes the propagation of light in terms of rays. This approach is particularly useful when dealing with lenses, mirrors, and the formation of images. The basic assumptions of geometrical optics are that light rays travel in straight lines in a homogeneous medium, bend at the interface between different media, and can be reflected or absorbed at surfaces. These principles allow us to predict and analyze how light behaves in various situations, such as when it passes through a lens or bounces off a mirror. The behavior of light in geometrical optics is governed by three fundamental laws: the law of rectilinear propagation, the law of reflection, and the law of refraction. The law of rectilinear propagation states that light travels in straight lines in a uniform medium. The law of reflection explains how light bounces off surfaces, while the law of refraction describes how light bends when passing from one medium to another. These laws are unified under Fermat's principle of least time, which states that light always takes the path that requires the least time when traveling between 2 points. Fermat's principle, formulated by Pierre de Fermat in 1658, is a cornerstone of optics. It states that when light travels from one point to another, possibly through different media and after multiple reflections or refractions, it chooses the path that takes the least time. This principle can be extended to say that the path taken is one where the time is stationary. It could be a minimum, maximum, or simply unchanged by small variations. Fermat's principle provides a unified way to derive the laws of reflection and refraction, and helps us understand why light behaves the way it does when encountering different materials. When a light ray strikes a smooth, polished surface such as a mirror, it bounces back into the same medium. This phenomenon is called reflection. The first law of reflection states that the incident ray, the reflected ray, and the normal to the surface at the point of incidence all lie in the same plane. This can be visualized by imagining a light ray hitting a mirror and bouncing off. Both the incoming and outgoing rays, as well as the perpendicular line at the point of contact, are all contained within a single flat surface. The second law of reflection states that the angle of incidence is equal to the angle of reflection. In other words, when a light ray hits a reflective surface, the angle at which it arrives, measured from the normal, is exactly the same as the angle at which it leaves. This law can be derived from Fermat's principle, which tells us that light always takes the path of least time. The equality of these angles ensures that the path is indeed the shortest possible between the object and its image. Refraction is the bending of light as it passes from one medium to another, such as from air into water. The first law of refraction states that the incident ray, the refracted ray, and the normal to the surface at the point of incidence all lie in the same plane. This law helps us visualize how light changes direction at the boundary between two different materials, and is fundamental to understanding how lenses and other optical devices work. The second law of refraction, known as Snell's law, states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant for a given pair of media. This constant is the refractive index, which quantifies how much light bends when entering a new medium. Mathematically, Snell's law is written as mu1 sin I equals mu2 sin r, where mu1 and mu2 are the refractive indices of the first and second media, respectively. This law is essential for understanding how lenses focus light and how optical instruments are designed. The refractive index is a measure of how much light slows down and bends when entering a medium. It is defined as the ratio of the speed of light in a vacuum to the speed of light in the medium. The absolute refractive index depends on the nature of the medium, the wavelength of the incident light, and temperature. When light passes from a rarer to a denser medium, it bends towards the normal, and when it passes from a denser to a rarer medium, it bends away from the normal. This property is crucial for the functioning of lenses, prisms, and optical fibers. Total internal reflection occurs when a light ray travels from a denser medium to a rarer medium and the angle of incidence exceeds a certain critical value. At this point, instead of refracting into the second medium, the light is completely reflected back into the denser medium. This phenomenon is the basis for many optical technologies, including fiber optics. The critical angle depends on the refractive indices of the two media involved, and total internal reflection only occurs when light moves from a higher to a lower refractive index. Optical fibers are thin strands of glass or plastic that transmit data using light pulses. They rely on the principle of total internal reflection to guide light along their length, even when the cable bends. Optical fibers are preferred over metal wires for data transmission because they offer higher bandwidth, lower signal loss, and immunity to electromagnetic interference. The core of the fiber carries the light, while the cladding with a lower refractive index keeps the light contained within the core. An optical fiber typically consists of a central core made of glass or plastic, surrounded by a cladding layer with a lower refractive index. The cladding reduces scattering losses, adds mechanical strength, and protects the core from contaminants. The combination of core and cladding ensures that light signals remain confined within the fiber, allowing for efficient and secure data transmission over long distances. Optical fibers can be classified based on their refractive index, materials, and mode of light propagation. Step index fibers have a uniform core refractive index, while graded index fibers have a refractive index that decreases with distance from the core. Materials can be plastic or glass, each with specific applications. In terms of propagation, single-mode fibers are used for long distances, while multimode fibers are suitable for shorter distances. These combinations allow for various types of optical fibers tailored to specific needs. Optical fibers transmit data by guiding light pulses through the core using total internal reflection. Even when the fiber bends, the light is reflected back into the core by the cladding, ensuring minimal signal loss. The system includes a transmitter to encode light signals, the fiber itself, a receiver to decode the signals, and regenerators for long-distance transmission. This technology allows for high-speed, secure, and efficient data transfer over vast distances. Optical fibers offer numerous functional and physical advantages over traditional metal cables. They provide higher transmission bandwidth, allowing for greater data transfer rates. Power loss is minimal, making them ideal for long-distance communication. Optical fibers are immune to electromagnetic interference and electrical noise, ensuring secure and reliable data transmission. Physically, they are lighter, more flexible, and occupy less space than copper cables. Additionally, the raw material glass is cheaper and more corrosion-resistant, contributing to the longevity and cost-effectiveness of fiber optic systems. Despite their many advantages, optical fibers do have some drawbacks. The initial installation cost is higher compared to metal cables, and more repeaters are needed for very long distances. Optical fibers are also more fragile and require additional protection, such as plastic sheaths, to prevent damage. These factors must be considered when designing and implementing fiber optic communication systems. Optical fibers have a wide range of applications in modern technology. They are used in telephone systems, submarine cable networks, computer networks, CATV systems, and CCTV surveillance. Optical fibers also play a crucial role in emergency services, hospitals, schools, and traffic management systems. Their high capacity, security, and reliability make them indispensable in both industrial and everyday settings. Let's look at an example to understand how refractive index affects the speed of light. If the refractive index of glass is 4.3, and the speed of light in glass is 2 times 10^8 ms, we can calculate the speed of light in vacuum as 4.3 times 2 times 10^8 equals 2.67 times 10^8 ms. Similarly, if the refractive index of water is 3.2, the speed of light in water can be found using the same principle. This demonstrates how light slows down when passing through different materials, a key concept in optics. Suppose the refractive index of water with respect to air is 4.3 and that of glass is 3.2. To find the refractive index of glass with respect to water, we use the relationship between the three media. The calculation shows that the refractive index of glass with respect to water is 9.8. This kind of calculation is essential in designing optical systems where multiple materials are involved. Let's apply Snell's law to a real-world scenario. If a light ray in air has an angle of incidence of 45 degrees and the angle of refraction in glass is 30 degrees, the refractive index of glass can be calculated as n equals sin 45 degrees slash sin 30 degrees equals square root 2 slash 0.5 equals 1.414. This practical use of Snell's law helps us determine how much light bends when entering different materials. Let's clarify some important terms in optics. A beam is a group of rays. The angle of incidence is the angle between an incoming ray and the normal to a surface. The angle of reflection is between the normal and the reflected ray, while the angle of refraction is between the normal and the refracted ray. Homogeneous means of the same kind, and iterative refers to something repeated frequently. Understanding these terms is essential for mastering the concepts of optics. Interference is a phenomenon where two waves superpose to form a new wave of greater or lower amplitude. In optics, interference occurs when two coherent light waves combine, resulting in patterns of bright and dark bands. This effect is not limited to light, it can also be observed with sound, water, and other types of waves. The key to interference is coherence. Waves must have a constant phase relationship and the same or nearly the same frequency. For a stable and clear interference pattern to form, two main conditions must be met. First, the sources of the waves must be coherent, meaning they emit waves with a constant phase difference. Second, the waves should be monochromatic or of a single wavelength. When these conditions are satisfied, the resulting interference pattern is stable and predictable, allowing for precise measurements and observations in experiments. Constructive interference occurs when two light waves superpose in such a way that their crests and troughs align. This results in a new wave with a larger amplitude, producing bright bands in the interference pattern. Constructive interference is a key concept in understanding how light can be amplified or reinforced in certain regions, leading to the formation of bright fringes in experiments like Young's double slit. Destructive interference happens when the crest of one wave coincides with the trough of another, resulting in cancellation and a wave of zero amplitude. This leads to dark bands in the interference pattern. Destructive interference is just as important as constructive interference, as it explains the alternating bright and dark fringes observed in many optical experiments. In 1801, Thomas Young performed a groundbreaking experiment demonstrating the wave nature of light. By allowing light to pass through two closely spaced pinholes, Young observed an interference pattern of alternating bright and dark bands on a screen. This experiment provided strong evidence that light behaves as a wave, as only waves can produce such interference patterns. The double slit experiment remains a classic demonstration in physics classrooms today. The interference fringes observed in Young's experiment can be explained by considering the path difference between the two waves arriving at a point on the screen. If the path difference is a whole number multiple of the wavelength, constructive interference occurs, resulting in a bright fringe. If the path difference is an odd multiple of half the wavelength, destructive interference occurs, resulting in a dark fringe. The distance between consecutive bright or dark fringes is known as the fringe width, which depends on the wavelength, the distance between the slits, and the distance to the screen. Newton's rings are a type of interference pattern formed by the reflection of light between a spherical surface and an adjacent flat surface. When a plano-convex lens is placed on a flat glass plate, a thin film of air is trapped between them. The thickness of this air film varies from the center outward, creating concentric bright and dark rings when viewed under monochromatic light. Newton's rings are used to study the properties of lenses and to measure the wavelength of light. In the Newton's ring experiment, a plano-convex lens is placed on a flat glass plate, and monochromatic light is directed onto the setup. The resulting interference pattern is viewed using a microscope. The diameter of each ring can be measured, and the wavelength of the light can be calculated using the known radius of curvature of the lens. This experiment is a practical application of interference and is widely used in optical laboratories. Polarization is the process by which light waves vibrating in different planes are made to vibrate in a particular plane. Ordinary light is unpolarized, meaning its vibrations occur in all directions perpendicular to the direction of propagation. Polarized light, on the other hand, vibrates in a single plane. Polarization is a unique property of transverse waves, such as light, and does not occur with longitudinal waves like sound. Light can be polarized in different ways. Linear polarization occurs when the electric field vibrates in a single plane. Circular polarization happens when two perpendicular waves of equal amplitude and a 90 degrees phase difference combine, causing the electric field to rotate in a circle. Elliptical polarization is a more general case, where the amplitudes are unequal or the phase difference is not exactly 90 degrees. resulting in an elliptical motion of the electric field vector. Polarized light can be produced from unpolarized light using several methods, including reflection, refraction, scattering, selective absorption, and double refraction. Each method exploits different properties of light and materials to filter or align the vibrations into a single plane. Polarization is widely used in sunglasses, photography, and scientific instruments. Brewster's law describes the angle at which light reflected from a surface is completely polarized. The law states that the tangent of the polarizing angle is equal to the refractive index of the medium. At this angle, the reflected and refracted rays are perpendicular to each other. Brewster's law is important in designing polarizing filters and understanding natural phenomena like glare reduction. Malice's law states that when completely plane polarized light passes through an analyzer, the intensity of the transmitted light is proportional to the square of the cosine of the angle between the transmission axes of the analyzer and the polarizer. This law is fundamental in understanding how polarizing filters work and is widely used in optical experiments and devices. Diffraction is the bending of light as it passes around the edge of an object or through a narrow opening. The amount of bending depends on the size of the opening relative to the wavelength of light. Diffraction explains phenomena such as the silver lining around clouds and the colored bands seen around the sun or moon. It is a key concept in understanding the limits of optical resolution and the behavior of light in various environments. For noticeable diffraction to occur, the size of the obstacle or opening must be comparable to the wavelength of light. In the case of a straight edge, the edge must be very sharp and narrow. For a thin hole, the diameter should be extremely small on the order of the wavelength. These conditions are necessary to observe clear diffraction patterns, which are used in various scientific and engineering applications. There are two main types of diffraction: Fresnel and Fraunhofer. Fresnel diffraction occurs when the light source and the screen are at finite distances from the obstacle, resulting in curved wavefronts. This type is observed with straight edges, fine wires, and narrow slits. Fraunhofer diffraction, on the other hand, occurs when the source and screen are effectively at infinite distances, producing plane wavefronts. Both types are important in understanding how light interacts with objects and apertures. Fresnel diffraction is observed when the light source and the screen are at finite distances from the obstacle. The wavefronts are generally spherical or cylindrical, and the resulting diffraction patterns are more complex. This type of diffraction is commonly seen with straight edges, fine wires, and narrow slits, and is important in understanding the behavior of light in everyday situations. Fraunhofer diffraction occurs when the light source and the screen are effectively at infinite distances from the obstacle or aperture. The incident wavefronts are plane, and the resulting diffraction patterns are simpler and easier to analyze mathematically. Fraunhofer diffraction is widely used in laboratory experiments and in the design of optical instruments. Optics is a vast and fascinating field that explains many phenomena we encounter daily, from the colors of a rainbow to the functioning of cameras and fiber optic cables. Understanding the principles of reflection, refraction, interference, polarization, and diffraction allows us to design advanced technologies and appreciate the beauty of light. The study of optics continues to drive innovation in science, engineering, and medicine. Let's quickly recap some key terms: beam, a group of rays; angle of incidence, the angle between an incoming ray and the normal; angle of reflection, the angle between the normal and the reflected ray; angle of refraction, the angle between the normal and the refracted ray; homogeneous, of the same kind, iterative, repeated frequently. Mastery of these terms is essential for further study in optics. For those interested in exploring optics further, several excellent textbooks and resources are available. Some recommended titles include A Textbook of Optics by Braille, Optics by Satya Prakash, and Introductory University Optics by Phi Learning. These resources provide in-depth explanations, mathematical derivations, and practical examples to deepen your understanding of the fascinating world of optics. In conclusion, optics reveals the remarkable properties and behaviors of light, from its dual wave-particle nature to its ability to bend, reflect, interfere, and polarize. These principles not only explain natural phenomena but also underpin many modern technologies, from fiber optic communication to advanced imaging systems. By understanding optics, we unlock new possibilities for innovation and gain a deeper appreciation for the wonders of the physical world.